Today we're going to open up with astronomy, an excellent topic to begin with as we see the remarkable revelations coming from the James Webb Telescope. And as the astronauts are saying, you know, you haven't even finished rewriting the astronomy books from Hubble, so you happen to do it all over again with James Webb. It's, again, a very exciting time to be in this business. And today with us we have panelists who are going to speak to this, particularly on the Astro 1 and Astro 2 missions, STS-35 and STS-67. And we're going to lead off with our first guest today, astronaut John David Bartoe. John David is an astrophysicist, and he was involved on the ground with Astro 1 and Astro 2. And of course, he flew on STS-41F in 1985. The only mission I will recall that had an abort to orbit, when one engine went out early, and they got up on orbit and had to daily rewrite the flight plan. But John David is with us here today, originally from Abington, Pennsylvania. That flight on 51F was launched in July of 1985 and came back about 8 days later, and was a remarkable mission. And again, the beginnings of the extension of our reach into space as far as astronomy was all concerned, and the shuttle program was proud to have supported those efforts. Scott Vangan is he's sharing going to share some of the backstories about the engineering issues that were involved in these missions. Scott has had extensive hands-on operational experience with various spaceflight payloads, particularly astrophysics experiments designed to explore the electromagnetic spectrum from cosmic X-rays through ultraviolet and into the infrared. These gentlemen today are going to open up what I'll call some of the secrets of the Astro payload, a payload that was flown on both missions by our good friends, the late Sam Durrance. And in looking at this picture up on the screen now, I will recall this is similar to a picture that Sam used in his presentations to describe his first view out the window. And the thing I'll say that stands out about Sam in my memory was that every time he described that first sight out the window, you'd swear he'd seen it just yesterday. It was always that new, it was always that fresh, and it was always that exciting. And we remember Sam for his passion, for his kind manner, and for his good friendship. Did the lights go out, or am I having a stroke?
Is that okay?
You don't do that to somebody who's 68 years old.
Ed McMahon just had a big hook.
Well, gentlemen, welcome here to the panel today, and we look forward to hearing your recollections and to your story. So please take it away, guys.
All right, good morning. Testing, can you hear me?
No.
Oh, microphone, I guess there we go. I couldn't be more honored to be with my friends, colleagues, and lifelong relationship with these two gentlemen with me, John David Bartoe and Mike Haddad. And then a thank you to all of you to come join us today. We're excited to tell you the Astro story. And what is unique about Astro, amongst every mission has its stories, but there was an Astro 0, and we'll tell you about that. And there's actually an Astro 3, which is something that you may not be aware of. Now, these are informal titles, of course. There really only was Astro 1 and 2, but we affectionately refer to them as 4 different missions, and you'll see why as we tell the story. So Mike and John David and I will step through some slides, and at the end, to give you an opportunity for Q&A. The Space Lab platform allowed Astro to fly, and for you that are familiar with space history, know Space Lab was a partnership with the European Space Agency. And this was a big deal back in the late 70s when they signed an agreement with ESA to participate. And at the time, it was $1 billion+ program for ESA. Put it in today's monies, you know, it's a magnitude more. But it was the first time that NASA basically took a major program, i.e. the shuttle program, and joined at the hip with the Europeans to develop hardware that would define the next 2 decades of space science platform. And it had a combination of pressurized modules to allow shirt-sleeved science experiments, and many of those missions had been flown, in addition to non-pressurized payloads, and Astro's one of them, meaning it's exposed in the payload bay of the shuttle. And the hardware was very successful. 2 dozen different payloads flew under the Space Lab banner, and it defined the space science environment for decades. It was replaced ultimately with Space Hab, followed then, of course, by the space station. So that kind of sets the platform with this hardware base that ESA provided, and the NASA infrastructure of the shuttle, amongst other hardware, is the Astro missions. And likewise, in the late 70s, they were saying, what are we going to do with this space platform called Space Lab? Well, we're going to have these different multidisciplinary sciences, but we also want to do some dedicated missions. And one of those was Astro. Hey, let's have a space observatory platform that we can fly and bring the payload back and improve the detectors and the capabilities and fly it over and over again. And to the science community, this had a lot of appeal. Because up to this point, you either flew sounding rockets that were good for a few minutes as a suborbital, or a dedicated orbital science platform, but you never got the equipment back, and not nearly the capability you could have with the orbiter. And so after a review process, the selection was made that they would fly 3 telescopes. They were decided through a process with peer review by astrophysicists, and the dedication for Astro would be focused on UV, ultraviolet. The 3 telescopes picked were the Hopkins Ultraviolet Telescope out of Johns Hopkins and developed by the Applied Physics Laboratory up in the Baltimore area, the Ultraviolet Imaging Telescope out of the Goddard Space Flight Center in Maryland, and last but certainly not least, probably the most fun title you'll ever hear on a space science payload, called Whoopee, the Wisconsin Ultraviolet Photopolarimeter Experiment. And you know how NASA picks acronyms. You find a neat word and you work your way backward. They've got to win. In fact, I know this personally because I work very closely with this team. They got a lot of pushback from NASA. And they wouldn't budge. They said, Whoopee is what it is. You cannot change it. And then they said, well, you need to change it to 3 letters. How about whoop? And then they thought, no, okay, we'll stick with it. So why space? Why ultraviolet? Well, the answer is embedded in the physics of the necessity to explore the various aspects outside of what our eyes can see. The visible light, as amazing as it is, and we all take pictures and we all have concluded things as scientists with what the visible light tells us, but there's secrets to be unleashed when you look into the different bands: ultraviolet, X-rays, gamma rays, infrared, radio. These are all different frequency component changes of the electromagnetic spectrum. Our eyes are a little slit on the universe. And so the ultraviolet is going to give us something new in learning about the world, the universe, the galaxy that we live in. Okay, so we've decided we're going to look in the ultraviolet. Well, let's just do that from Earth. Well, it doesn't work that way. It turns out on the graph on the right, you'll see that different bands or frequencies of light, components of light, some penetrate the Earth, visible light, surprise, surprise. Well, we evolved as all life to deal with visible light because that's what makes it to the surface of the Earth. But no joy for ultraviolet. And you may go, wait, I put on sunscreen to protect me from UV, and that's true. There is some very near-band ultraviolet light that comes down and something you should protect yourself from. But this big band that was of interest to the scientists, it doesn't make it to the surface. So ipso facto, we need to go up. And the shuttle took the Astro payload up about 190 nautical miles above the Earth, which is way above the atmosphere, which gives us the clear access to what we wanted to look at. And just, there's 1,000 examples, but I picked one. This is Galaxy M33, and we were talking about visible and ultraviolet. This is what you see if you grab a telescope and go outside, and you'll see something like this with a time exposure. with an ultraviolet telescope in space, you get this. And you think, okay, they look similar but different. And that's the key in science. There are similarities, but there are also some differences. In this case, it shows star formation. And why is that important? Well, it teaches something us about our galactic history. Where do stars come from? How do they live their lives? How do they die? Are there different types of stars? As there are a variety of people, there's a variety of stars. And so, without going too far into the science aspect of that, and I know we have another gentleman from FIT here who will be talking about as astronomy, that sets kind of the stage for why we do space-based observations. Here's an artist's concept. This is before it flew, or what it would look like, but you can't, back when we flew, you didn't have something that could go take the pretty picture. You know, we were spoiled now with space station and the like that has that. So this is the best we have. This is the platform. The Astro telescopes, Wisconsin, Whoopee, Hut, and UIT, they're all mounted on this structure here, co-aligned, that they can point to a particular place of a target. And there's a pointing system down in the payload bay of the orbiter, part of the Space Lab system. And JD is going to tell you more about that in a few minutes. On Astro 1, we also had another payload that joined us, an X-ray telescope. So again, a different part of the frequency spectrum. So a nice complement. And I can't emphasize enough, this was very new and unique. We're going to fly a space observatory on the orbiter, spend a week, 2 weeks in space, bring it back, refurbish it, and do it again and again. And the original plan was to do that 6 times. Well, like all good plans, things happen. It was truncated down to 3, and in the end, unfortunately, only 2 missions. But we're going to tell you about the 2 missions that flew and the good science that occurred to it. We'll touch on the actual flight times here in a minute, but let's now talk about what it takes to pull off a mission like this. I already mentioned the Space Lab hardware. The Astro payload was mounted on this strong back of something called the cruciform. If you look at it from the top, it looks like an X or a T or a cruciform. And the co-alignment of these telescopes is amazing. And Michael, can tell you a little bit about that. But when they put the telescopes on, you want it so when we point in a place, even if you're off by just a fraction, tiniest fraction of a degree, you're going to look at 2 different things. So the alignment of that, to fly that, a precision package, but then put it in the orbiter that takes the shaking of the launch, get on orbit, deploy it, point to a precision of an arc second, we'll talk about what that really means, and then stow it again and rinse and repeat and do that multiple times is rather amazing. So the IPS is what did that magic, called the Instrument Pointing System. And it was developed by the Germans, Dornier Systems, and part of the Space Lab delivery, and it provided that accuracy that we talked about. This thing called the Igloo is all the avionics, if you will, the smarts, the big computers at the time, 64K, woo! Yeah, that's true, that's what's in there. And so, humble as it was, think, this is 1970s technology, is pulling off something rather remarkable. The 3 telescopes I mentioned were mounted on the cruciform structure that's then integrated onto the IPS, 2-pallet train. I mentioned that the broadband X-ray telescope flew along, but it only flew on the Astro 1 mission. It had its own unique aspect to it. Here's a better graphic that shows the details of how it all bolted together. I point out, in addition to the 3 telescopes, there was something called the optical sensor package. These were 3 star trackers that would then, the way this worked is you think you know where you want to look, you verify that's where you're looking, and then the star trackers lock on. And no matter what happens to the shuttle underneath or while the shuttle's orbiting the planet, you stay locked on your target. And again, 1970s technology, we all take CCDs and our cameras for granted. This is about a 500-pound structure that now, if you flew it, it'd probably be about the size of this laser pointer. But that's what we had at the time. And one other thing I'll mention is this integrated radiator system. All of this stuff is exposed to space, so it either gets very hot or very cold, but we couldn't put on any active cooling system on it. because of the freon lines and stuff necessary to that, would have affected the pointing accuracy and the tracking capability. So some very, very smart thermal engineers figured out a way to do this all passively. Let's talk about the instrument pointing system. And I think this is a time that JD, you'd like to elaborate? And I might point out, he's humble, he flew the IPS for the first time on his mission on Space Lab 2. It looked at the sun, and now it's in stellar mode looking at targets, but the pointing system is the same. JD?
Yeah, why don't you flip one more slide. So the reason I was involved in Astro 1 is because I flew the instrument pointing system on Space Lab 2, and I got a call saying, hey, would you like to come help us out since you know a little bit about this? And so that's how I got the role as the APS, which is basically the payload version of what we call CATCOM in Houston, in Huntsville. It's the APS position is one who talks to the crew. And this is an interesting slide because I want you to look at the bottom where it shows that 1 arcsecond means that you can point at a dime 1 mile away. Okay, think about that for a minute. Point at a dime. Where's your pointer? Okay. So, and you're going to hold it by the end. Okay. Now, nobody in their right mind would build a telescope where you hold it by the end. You always hold it by the center of mass. But that doesn't work. There's no room to do this. So they just came up with this design to hold it by the end and point it at a dime a mile away. Now, I went to Dornier, which is in Friedrichshafen, Germany, several times during the first production and design of the IPS. And I have to tell you, I did not think it was going to work. I thought this was pretty much a dream to be able to point this thing this accuracy. But they did some clever things. They use a thing that if anybody in here has ever worked with servo control loops, you've heard of the famous Kalman filter, which is a special piece of software you use to get the noise out of the system so you can try to find the real information. And they did another really clever thing, and that was they put in a forward loop system. And by that I mean, the problem was, even though you're in 0G, so it's not that kind of a problem, it's not like it's going to fall over. However, when the orbiter moves, this is going to move. So rather than trying to chase the star all the time up there when it moved, they put an accelerometer right at the base, and when they would see the motion coming, they would immediately feed that into the system to keep it pointed, to move it and keep it pointed in the correct position. This was the thing that made it actually work in my mind. If they had not put this extra accelerometer down on the base and fed that into the software. Now, did you want to talk about the problem with it? No, that's comes
coming
later.
up in a little
Okay,
bit, yeah.
well, hold on. All right, go ahead.
Okay. This is going to be a test later, so you... This makes the point that JD was mentioning. It's a very advanced control system with lots of loops. There's the feed forward loop with the accelerators. There's a feedback loop with gyros. There is the optical sensor package that I mentioned that tracks stars. If that isn't enough, they had a separate thing called an Astro star tracker that independently fed into this, and all of this with this computers technology from the 70s. And it worked. It's some very smart people learned from Space Lab 2 what worked, what didn't work, approved upon it. On Astro 1, there was some issues. We worked through that, but it got even better then for Astro 2. As you do with control systems, you learn more of the behavior. It was rather an impressive package. But let's shift gears now and talk a little bit about what does it take to get these telescopes and the IPS and all the Space Lab hardware together. Mike, do you want to elaborate a little bit about that?
Yeah, okay, just taking a look at this first image. This is Whoopi. Basically, it came in this horizontal structure here. And as you can tell, it's basically did a lot of the work horizontally, but our configuration for the cruciform was to integrate vertically. So of course, now you got to go from horizontal to vertical, and that's what this device did. It actually would rotate it to vertical, and this part here was actually part of the support structure, which also became the lifting sling. That's separated from the main support structure. That's what you see over here. It's kind of Whoopi being lifted up with the support structure to be installed on the cruciform. Again, you see everybody's in white. Maintain cleanliness 100K max. It was always better than 100K, 100,000K. So as you can see, everybody basically suited up here as we put Whoopi on. And that's the first telescope. This is the basic cruciform structure with the Whoopi going on first. And of course, this is up in the operations and checkout building, which is actually the Neil Armstrong now operations and checkout building on the southern end of Kennedy Space Center. This is in what's called the low bay area, which you don't think is low because it's like 80 feet high. But the high bay area was like 100 feet high. And so this is basically the main integration where all this, the main building where all this integration took place. I mean, the pieces would come in literally from all over the world and would all see each other for the first time, a lot of times here in the operations checkup building. And our job was to install that. Basically, myself and some other gentlemen in the audience, our job was, from the mechanical group, was to install this. Scotty and John and them basically made them work, make sure they worked all the stuff out together. This is just a good picture of, and this was repeated, and now this is the hut. And you can see how huge this thing is. Again, came in on a horizontal, and this structure actually was neat. This one, where Whoopi had this structure that rotated, and then you pulled it out. This one actually, the lifting sling is what rotated. If you see up here, I would go from horizontal to vertical, and Louis Delgado is going to be on the panel in the afternoon. He's actually, I think this is him here. Again, this is back in the early 1980s, and again, this is a large building, as you can see. This is how we lift hut with an overhead crane and what we call the hydroset, which is basically for the weight. And that, again, would be then lifted up and put on the cruciform. And it was a series of how do you put these on? You know, what goes on what order, and then also, like Scott was mentioning earlier, the alignment. We had to put these things on and align them within that arc second. And so what they did is in some of the supports, basically this had like 3 supports, there was actually like a metal wedge with threaded. And so as you move that wedge in and out, would adjust the alignment, and so you had the precise alignment. So not only did you have to put this on, but you had to align it at the same time. So this is just a picture of showing that. And then this is UIT, again, came in the horizontal. But this is a pretty good one because this is when we were actually rotating the whole cruciform. We had to go from horizontal to vertical. Well, when we did that, somebody didn't take into account there's this radiator that the sling just kind of doesn't pass it. So I stuck a web strap in it to pull the sling kind of this way as we were rotating it, just so it wouldn't interfere with the rotation. So that was just one of the problems we had with putting these instruments mechanically on. And then this is the whole package. This is once the package is together down in the, this is the west part. You're kind of looking west on the building here. And then we had to move basically to these other integration stands. Kind of the way this building worked was we'd start at one end with the piece parts and think of it like an assembly line. As you worked down the building, it became more and more integrated to when it got to the end of the building, it was basically ready to go to the shuttle. And that was our job, was basically making sure that we fix all the problems here. You don't want to find problems with the shuttle. It's the last place once you're in the shuttle. So our job was to make sure that we found everything here. And this is just moving the whole telescope package down into the, farther down into the building now. Now, one thing I want to point out here is, I think that's the wide field camera right there, isn't it?
I think so.
Should I talk about that now?
Sure, why not?
Okay. Well, Astro originally was supposed to fly in March of '86, which is going to be observe Halley's Comet. Well, this experiment here, in fact, that was the experiment I worked on. I worked on a lot of some of the structure cabling and electronics, but that was my experiment. It was a wide field camera that was supposed to look at the Halley's Comet in '86. Okay, so this is a good picture of that completely integrated going into the, and here's a kind of the face of the IPS we talked about earlier. So there's an interface between this structure and the IPS, and this is basically that process of putting those two together. Again, we didn't fly, we'll explain later, but the wide field camera didn't fly. But this is a good picture of a completely integrated, what we call Astro Zero.
If I can inject your mic, back to what JD was talking about, the instrument pointing packet, or instrument pointing system, the Dornier system, you notice this round surface. And as Mikey said, this integrated payload gets mated to that. That's kind of half true. They're mated in orbit, but for launch, they're separated by a few inches. And you go, wait, how are you going to put these two together? Well, they're separated for launch because we mentioned before, the jiggling. Imagine all that mass tied in, and the poor little gimbals holding that IPS wouldn't survive. So some very smart engineers said, let's keep them separate. And when they get on orbit, these payload latches, which you can't see, they're kind of on the side, they hold these trunnions for launch, but they're released, and there's 3 cables that come from the IPS over to the back plate of the integrated cruciform with the telescopes. And motors pull those into sockets and then clamp down, and then you're good to release and deploy the IPS. And the reverse is true. When you're ready to come home, you stow this whole assembly back in the payload bay, you release those clamps, and you go, well, you can't push on a rope. So how do you separate them? It turns out that there's some little leaf springs that just give it a little bit of push, and then the payload clamps are designed to grab those cruciforms and pull it in and secure it for stowing. It's a mechanical piece of art that they did this. The precision you need for pointing, that was discussed, but the rigors of the launch of the shuttle working together. I think, JD, you wanted to talk about testing?
Yeah, this is a pretty interesting picture. On the left, let's see,
Jeff.
that's Jeff Hoffman sitting there, and then the 3 PSs are behind Jeff here. They're sitting at a console, exercising the instruments, and on the right is one of the teams, instrument teams. It's the Whoopie team.
See that long-haired hippie?
Yeah, I don't know who the guy is.
I
with
wouldn't
all
trust
that
you
beard
at
there.
all.
But I have to tell you something about, so this operation was called Level 4, that was because it was the 4th level leading up to Level 1. And it turns out that this was probably the most important thing that NASA ever did to decide that they would let this happen. Originally, the plan was a phrase called ship and shoot, which means your instrument comes to the Cape, you bolt it on, and you launch. No testing. Saves lots of money if you do that. And the people at the Kennedy Space Center worked really hard with NASA headquarters and convinced them this is not going to work. Because when everything comes down here, it's not going to be perfect, and there are going to be lots of problems. And it was proven with the very first Space Lab mission. The work that had to take place on Space Lab 1 here at the Cape to make it actually really ready to fly. So the other interesting part is, when we were doing our post-flight recording, where you sit down with George Abbey and you write your little post-flight report, I remember specifically that one of the astronauts said, the very best training I got was at Level 4 at KSC, because I was actually sitting at a console and controlling the real hardware. And I learned way more there than I did in the simulators back in Houston.
That says a lot, sorry.
Thank you.
But it's a good point, and it takes a team. This is a part of the KSC payload processing team for Astro 1. This is at the far end of the building that Mikey was talking about, in that assembly line. It's called the site stand. It's the last stop before it goes out and joins the orbiter. And this particular picture shows the payload integrated there onto the pallets, and us all standing in the stand. Forgive the circles. At the time, I think we're trying to highlight a couple of people there in particular. But the KSC payload processing team is a unique story. As JD and Mike said, to have NASA civil servants along with technician contractor support was very new, at least in the shuttle era. And it put a lot of trust on young engineers. Mikey, myself, and a few other gentlemen here today, we were just out of college. So think about that. We're GS7s and 9s, just starting our civil servant career. And in the case of myself, I was assigned the Whoopi experiment. So this multi-million-dollar experiment to a guy who just walked out of, undergraduate. It's a lot of responsibility, but when you're young, you don't know what you don't know, which is kind of good. You don't realize just how deep into the water you jumped. And it was the best, and I think you would hear this from anybody who worked level 4, the best work ever, because the responsibility is so high and the freedom to do your work with the help of others was immense. And it paid off. And what was unique also, I'll share, and I think Mikey and JD would concur, what's unique about the payloads group at the Kennedy Space Center is every payload was different. The shuttle had kind of a routine, and rightly so. You get it ready for its flight, but it had the same systems and kind of basic procedures to ready it and launch it. The payloads changed every single time. And each time was a new set of payloads from different developers, different countries, different nationalities, different ways of doing work. It's quite a story. So here's a good close-up picture in the site stand, cargo integrated test, ready to go. And here, Mikey, I'll point out wide field camera. So this would have been very, very early 1986. And if that date means something to you, you'll find out here briefly. Here's another picture of it integrated. This is Astro 1 actually, in the Space Shuttle Columbia. You're looking at the hut. That's a 1 meter opening aperture there. We're taking off the covers at this point. You see somebody on this J-pole access, which is in the orbiter processing facility to do that. This vertical structure here is the broadband X-ray telescope. You can see how close they are for launch. But of course, once they get on orbit, this gets deployed upward on that pointing system. And the BBXRT had its own 2-axis pointing system. Mikey, you want to talk about what happens out at the pad and maybe a little bit about the hut detector?
Yeah, sure. If you take a look at this image, this is actually now after, when we go horizontally in the orbiter, and the orbiter goes to the VAB, goes vertical, gets put to the stack and out to the pad. Well, this is actually showing Astro in the vertical. You can see everybody, this is standing up, and this now this is vertical. So what was horizontal now is vertical. I'm not going to hit you with this. And of course we got these covers on, and the idea was to protect the instruments. Again, you can see everybody all in full bunny suits. And you say, okay, well, some of them, they got their open ones, and other ones, they got these face things on.
Who's that guy with the mustache, Mikey?
I don't know who this guy is. That guy right
Yeah,
there.
he's in trouble.
Well, he's in trouble. I know what it's right, he's in trouble. See, because the idea here is no facial hair is supposed to be exposed. That's why you see some of the people, all these.
I think I pulled it down for the picture.
Basically, so you see the people here don't have any mustache or beard, and the ones that did have what we call eye hoods or face hoods. So you got the face hood for your whole face or your eye hoods. And so that's basically the only thing exposed. If you look, we got the latex gloves, and you got your sleeves are taped to the glove, nothing exposed. I mean, literally nothing. We, jumping through your face, and the idea is even a hair. Some of the payload we worked on, and this is kind of gross, but we couldn't even wear cologne or perfume because the outgassing would affect the optics in that. And so cleanliness was mandatory. We had to maintain this stuff clean. And what this shows is basically the covers that were basically on until late in the float the pad. I mean, this is probably within days of closing the doors before launch. We're starting to now pull the covers off. We're basically ready to close the doors for flight. So the last thing is get these covers off so we can go right in the door closure and keep the stuff as pristine as possible. So it's a great picture of Scotty and the whoopee team basically pulling off the whoop. But you can see they got the AST one up here, the hut, and all that. And again, you got platforms that tried to get us there, but as you can see, some of the covers were too far away, so you had these grabbers you got at home, and we had to use the grabbers to pull the thing down. And again, you want to be careful that you don't damage the flight hardware pulling the cover off. I mean, your days with the launch, all you need to do is mess up something on the hardware, and you just bought launch. And so this is a good picture. That's a great picture, Scotty. Kind of a closeouts at the launch pad just before the mechanical stuff just before you go, basically close the doors for flight.
Yeah. Thanks, Mikey. So let's talk about the Astro missions now. We've talked about what the science, why you go to space, what the payload is, the hardware, processing, the integration, the test. Let's talk about the missions. Astro Zero, the crew that never flew. How many of you heard of STS-41 If you have, then you know what Astro Zero is. So we were all dressed up, ready to go to the ball, and all the testing was complete, literally days to getting installed into the orbiter when, sadly, Challenger happened. We were the next on the runway, so to speak. Challenger occurred, and without going too deep into that, that affected a lot of things within the NASA family, not the least of which is it was a stand down for several years. And so, my goodness, we were all good to go, and what are we going to do in this meantime? In the case of Astro, well, let's take care of the science, the payload, and get ready for when NASA says we're good to go again. So 61E, this particular crew never flew. The pilot, the commander, and one of the mission specialists did not fly Astro subsequently. Of course, Ron and Sam as payload specialists did, in addition to Bob Parker and Jeff Hoffman did follow along. So during the stand-down period, we did a few things. We turned back the experiments to the principal investigators, the development team. Hey, there's no reason for NASA to hang on to this. The Hut telescope was returned to the Johns Hopkins folks. They put in better detectors and some new technology. Whoopi did some power supply mods. UIT made some improvements. But the space side systems needed some attention too. And I think this is a good point for JD to talk about 3 things that happened that if there's a silver lining to the stand down, you're about to hear it.
I'll talk about one, you talk about the other 2. You notice this circle here, it's kind of like a circle with an opening in it, or a bent horseshoe, however you want to think of it. And also notice this black piece on the back of this plate. So, and this is the big gimbal for the instrument pointing system. So this lifts up and it goes up through that opening, and then this serves as a bumper. The point of the bumper was you never want this telescope to hit the orbiter, to hit the sills of the orbiter. There was some talk about trying to do this protection via software, and they finally said, let's just make it mechanical. So it's guaranteed, we'll just put a bumper in. So this bumper assembly was the same pieces that were used on Space Lab 2, where I flew. And during the stand down, folks from Dornier came in to do some minor work on the gimbal latches system. And the lead mechanical engineer discovered something. I'm going to read his particular sentence that he wrote to me. He said, something in the position of the impact ring and the bumper seemed strange to me. And I had the impression that there was not enough clearance. He said, so I asked if we could install the ring on the second IPS, which was off to the side. And this was done, and it showed up that the gap in this ring was several millimeters too small. It would have been impossible to raise the IPS in orbit, and the mission would have been terminated immediately.
Wow.
So So this was just, you know, how the convolution of things in life come together here. If it had launched, if Astro Zero had launched on time, this never would have lifted out of the payload bay.
Wow. And we might mention, and Mikey knows this well because we have several examples during the shuttle program, where safety, you know, they have an important job and a lot of things to consider, but whenever we get a late, and I mean late in the processing flow request to put in a safety feature, it makes us nervous because we've been through all the testing. And when they came in late in the flow of Astro and said, as JD said, we're going to put in a different size bumper ring. He said, wait. Well, we did all the CAD models to the extent you can in the 80s, and it's going to work fine. Well, they made a mistake, and that would have been the consequences. And just a reminder, test is best, right? All the analysis that you can do up one side, down the other, but test is best.
So the crew says, you know, test as you fly, fly as you test.
So, had we flown right after Challenger, we would have gone up there. This would have been a major snafu for NASA, and one that we would have just had to pack up and come home. We had two other things we discovered during the stand down. Mike, you want to talk about the Lawrence bolts?
Yeah, they just basically, they weren't, anything that flies in the shuttle is the best of the best, basically. And you just think of bolts and nuts and washers. Same thing. I mean, we would inspect, we would get these bolts and nuts and washers and basically double bag cleanliness level requirements, and we would inspect the threads on each of these bolts, inspect the heads, and so basically there was a quality inspection, even though they were flight certified, we would always do one last inspection before we installed them. And well, we put them in and we found out that these bolts, basically, the way they were manufactured, I guess, wasn't to the NASA standard. And of course, after they're installed, what do? You gotta take them out and replace them. And then of course you got, okay, well, if you've got, say, 8 bolts holding the structure, well, you can't pull all 8 bolts out, then the structure basically comes apart. So you gotta pull one out, put a new one in, pull the second one out, put the new one in. So it was, basically that second bullet was, we had to replace those bolts before we flew.
Yeah, and the 300 some bolts, and remember the tightness, the tolerance on everything we just discussed? It was a real challenge. And likewise during this time, there was some concern about cable splices within the IPS, and we changed out, I can't remember the hundreds of splices associated with that. So the stand down gave us an opportunity to fix what was wrong and also improve on what we had. And so I mentioned where the telescopes came off. Wide field camera, unfortunately, was removed, as Mikey said, because our opportunity to rendezvous with Halley's has passed. It was going to be in '86. We'd have to wait decades later, so off came WOC. Sorry, Mikey, that was your payload. But we did get BBXRT added, which is, this is a graphic right here. I mentioned a 2-axis pointing system. I might mention what's unique about this, it launched with solid argon. Solid argon, not gas, solid. In fact, the engineer responsible for that is sitting in the back, Frank Valdez, and their team to get solid argon installed into this payload that was required for the X-ray telescope.
And maintain that up until launch. You know, how to keep something cold for many, many months at a time.
It's a fun little graphic. We're back with Astro the dog, Astro, if you remember him. So coming back. So what's old is new again, and yay, finally get to Astro 1, STS-35. And this, you know, the team now is kind of lean, mean, working machine. We really knew this hardware well. And the crew, we have a new crew now. The commander, Vance Brand, Guy Gardner is the pilot, and now Mike Lounge joined. The payload specialist remained the same, and Bob and Jeff came back. So this is the new crew, good to go. Little fun fact, you may or may not know, on Astro 1, STS-35, it had the record for the number of trips on the mobile launch platform. Out, back, out, back, out, back. There was a hydrogen leak associated with the 17-inch, I think, disconnect. And every time we roll out, they fuel up, leak, you have to roll back. It was a mess. We were going to launch in early December and it wasn't until, pardon me, early 1990, and it wasn't until December that we launched. It really was, and other missions went ahead of us because of this. And so Astro the robot dog, a little wounded, limping along, but here we get going, and we had a sense of humor with our shirts. This was the original launch date, and this is just a fraction, and you can see even that wasn't correct. We ran out of space on this particular shirt, but our motto always, don't worry, be happy. That was when the song was out, and you kind of had that. And hey, finally, we launched on board Columbia on December 2nd, 1990, and it was a night launch. We have to, it's astronomy, right? I'm going to do that during the day. And a beautiful shot out the aft flight deck, and here you see the optical sensor package. This is the UIT telescope, that's an integrated radiator system, the instrument pointing system, that's the avionics there, you see the end of the pallet. We're off and running, and we ran for 8 days and had great science. Some fun pictures. Again, deployed. This is Sam Durrance operating the laptops for controlling the payload, the flight crew picture. It's 2 shifts, if you will, red shift, blue shift, and so one group was sleeping while the other went, so 24/7 operations. I share a fun picture here. I think to the best of my knowledge, this was the first time we had kind of a teacher in space program. Sam and Jeff wearing a tie because teachers wear ties, did an astronomy mission in space, and it was well received and kind of set a precedence for future missions accordingly.
I'm going to make a comment here too. A couple of facts about Ron and Sam that you might not know. So I met Sam in the 1970s at White Sands Missile Range when we were both flying sounding rockets. I was studying the sun, he was studying the stars. And I had a really nice telescope. It just barely fit in an 18-inch diameter rocket, big mirror. And Ron rolls in, Sam rolls in with his telescope, which was this big. So we met each other for the first time, and he couldn't resist. He said, "My telescope is bigger than yours."
Telescope envy.
One more with Ron. So it's actually, during that same time period in the 1970s, Ron came into the Naval Research Lab where I was working to interview for a job opening that I had to work for me. And he made an excellent impression on us. However, he ended up being the #2 person in the choice, so he did not get selected. So if he had been selected and started working at NRL, he would not have flown Astro. So I think he always was kind of like, I'm glad that didn't happen.
That's great, John. So it takes a team. And the reason I put this up here is to remind you that we've been talking about Kennedy, we mentioned Johnson. This is the first time that the Marshall Space Flight Center was active during the mission in an op sense. There was something called the Payload Operations Command Center. All missions prior to this were run out of JSC. So this was a big deal that JSC handed the baton to Marshall saying, you've got the ball for the payload operations. There's still mission control, the flight director. At the POC, that's where the science team was and the space lab team that operated the hardware, between the HOSC, which supported it, and the POC, and then the science team. And JD, I think you had some.
Just one comment. I think that sometimes, if you ever watch on TV what's going on in mission control or the POC, it's kind of like watching grass grow. Not much excitement, but most of the camera shots you can't see people's lips, and there is a lot of activity going on between all of those people over the loops. And the first C in MCC and POC are pretty important, command and control. It is not the Mission Monitor Center. It's the Mission Control Center, right? And same for the POC. So there is serious activity going on there actually controlling these missions. And the people who work in this environment actually have a harder job than the people on orbit. I was a crew member on orbit, and I was the Marshall version of Capcom on the ground. It was harder to be the Capcom on the ground.
And so the mission was very successful, but not without its challenges. And we have a behind-the-scenes story for you here. And this is a big deal. Shortly into the flight, the computer interface called a data display unit, again, a YISA component, had a vector graphics display and a keyboard. These are the user interface for the astronauts. We had 2 of them on the aft flight deck. One went and failed by smoke. You never want to hear the call from the orbiter saying that they see and smell smoke. And the second one failed, and so the complete loss. Now we're going to tell 2 stories. One was the cause of this, and then how we rebound from it. I'll do the cause, and then JD was going to elaborate how we rebound from this. So when we got the first call down that we lost a DDU, you shut it down, right? That's the right thing to do. It's like, my goodness, what could this be? And at the time we didn't know. And they said, let's keep pressing with the other one. And then that one failed. In post-flight, when we got these things back and deintegrated them, they each had a little filter. Think of a little small HEPA filter that are on the bottom. It had been collecting, has a fan to draw through to cool, you know, the electronics. Because we sat so long on the ground, rolling back and forth than we planned, the regular maintenance swap out of the filter, instead of being, you know, only a month between swap outs, then was like 9 months. And add on top of that, we had additional testing. So Mikey and I and others were in there with our bunny suits, as we talked about, in addition to the flight crew with their blue suits. Well, when the filters came out, it was covered with fine white lint and blue lint that had accumulated during the 9 months. Of course, it didn't get into the filters right away, but in orbit, it all floats. The fan sucks it in. It blocked the filter. The filtered air stopped in a timing circuit in there, actually, and it overheated. And what you smelt was a resistor that was burning itself up. So there wasn't really a risk of a fire per se, but smoke is never a good thing. As you know, the joke, when you let smoke out of electronics, you let the magic out. And same thing, we shut it down. So now here we are, a day into the mission, and the crew interface for operating all this hardware is at risk. JD, what did we do?
Well, so at the POC, we started a discussion right away, and all of the experiment teams said, we can send all the commands from the ground here. You know, the crew doesn't need to, the crew was going to type in all the commands. We can send them all here from the ground. And the management choked on this idea. There was one position in the POC called command, and every single command that anybody wanted to send had to be sent by that individual. And we said, that is not going to work. We're talking about thousands of commands. You've got to let the teams who are expert at this, they've been commanding their instrument on the ground for years, let them command it. So finally the people at Marshall were convinced, and then they had to go to Houston and explain to Mission Control that we're going to let some crazy scientists send commands directly up to this instrument. And that took some convincing, but Marshall did convince Houston that this would work. Now, the problem was, though, you still had to do the fine pointing. And the one thing that was still working on board was the joystick for the pointing system. So there was a little joystick. And so we developed what I consider to be the world's largest servo loop ever created. And it goes kind of like this. First you get a star image, and then the instrument sends the data to the payload computer, who sends it to the orbiter computer, who sends it to the antenna, sends it up to the relay satellite 22,000 miles up in the sky, and then sends it back down to the White Sands receivers, and then over to the JSC computers, the Marshall computers, and then to the APS display in front of me. And then I can see where it's pointed. And now I can talk to the crew and tell them how to tweak the pointing. So we would sit there with a pencil. I'm looking at the screen, and it would drift down a little. I'd say up, and Sam would go boom on the stick. Left, and he would go boom on the stick. So if you ever listen to this recording, it's up, right, down, down. You think we were going crazy in the park. But this servo loop actually worked all the way back around, and it gave the opportunity, particularly for Whoopi, who had a small aperture. It was difficult to keep them pointed right on.
Yeah, and I might say, this is firm memory for me. I was at the POC on the Whoopi team, and distinct memory, and JD gets the credit for this. This loop is something he sketched out while he was sitting on council, and they were figuring out what to do with the loss of the DDU. And he came down to the science teams. He goes, I think this is how we can save the mission. And he had this sketch, and I asked if he had a picture of it, and what happened to it, JD?
Actually, it was destroyed in a flood in Houston in our house.
So we lost the original, which would have been great. That's something that should be in the National Archive, because it was that sketch, and I want to reemphasize the adaptability of the team, and it led to this. We rebounded, did great science, and this note on the right is very significant. I'm glad I have a copy of it. It's from Gene Kranz, and if you know that name, he is Mr. Flight, Control, Flight Director. I have been listening to you all day long, doing a superb job and writing the book on what real-time ops is all about. This is coming from the guy who heads up the JSC mission control.
Yep.
There is no doubt that you guys, gals, have a real handle on what you need to get the job doing, and without the bureaucracy trying to manage every step. You've moved out to get something big out of the mission. Keep going, and you'll write the shuttle textbook for the next generation.
Wow.
Coming from Gene Kranz, that's his best of praise. So you go back to what JD said, like, oh, no, we didn't train for this. We can't trust you to do this. To, my God, you guys did an incredible job in real time. And that built stock for Marshall, for the science teams, for decades to come. It's like, hey, we can expand beyond mothership MCC and bring in everybody to make the best out of it.
And one thing too, Scotty, you had to do that for each target.
Yes.
That loop had to be performed. Each target, you had to get ready for the next target, prepare after completing this whole sequence, to repeat it. Target after target after target for all those days.
Exactly.
And we set the record. There were over 10,000 commands sent from Huntsville during that mission.
Very successful mission, despite the challenges. In fact, we were rewarded with Astro 2. 5 years later, from 90 to 95, the same 3 telescopes, although slightly improved, as we said, between missions. They took advantage of that. A little fun fact, that with Astro 2, we learned a lot on Astro 1 that people are interested in astronomy, duh. But the Public Affairs Office wasn't ready for the onslaught of people wanting to engage with Astro. So when Astro 2 came along, they had real-time running commentary for every target. So back to JD when he says, if you watched the old NASA TV and just watching the Capcom, today's morning wake-up call is, we went to live running commentary of science, of why the target, what's coming back from the target, live shots into the POC. It was really quite a change.
I want to mention to that, because I was watching it myself, and I'm a mechanical guy, right? It was the best, I guess, on orbit, because they would show a target, they'd show a squiggly line come down, and the astronomers said, oh, this means this, oh, that means that, oh, and so they would describe what you're seeing. And so it was like, oh, I can't wait to see the next target. What did they find out when they pointed this star or this nebula? And it was like that for day after day. It was like your science lesson, real time. I keep telling them today, that was the best version of the POC and the crew and all that interaction to tell, hey, this isn't squiggly lines. This is what's happening. What does these squiggly lines mean?
And
it was amazing.
And I think that reminder, astronomy is something fundamental that we all kind of can relate to at some level. We all see the stars, we see the moon, we just saw an eclipse. We were kind of pre-wired to be interested in the cosmos, and so to have that commentary running with an Astro mission that's bringing in the science was brilliant. I think PAO did a nice job on that. Here's the STS-67 crew, same Sam and Ron as payload specialists, but we brought in a new flight crew, Steve Oswald and Bill Gregory, commander and pilot, along with Tammy Jernigan, the payload commander, and John Grunsfeld. His first mission, you probably know John. He went on to be a Hubble walker and astronaut extraordinaire in the Hall of Fame. And Wendy Lawrence. It was their first space flights, Wendy and John. And yours truly got picked as an alternate payload specialist, which was a real honor. My work on Astro 0 and 1, if you will, apparently bought some trust with the science team, and when Ken Nordzik decided he had every right to fly as a payload specialist on Astro 2, but he chose not to. He was the proverbial scientist who the science is first, flying is second. Ron and Sam would kind of put it the other way, but we can relate to that, right? And so when Ken stood down, I competed with others and was fortunate enough to be selected. And so I trained for a year and a half with the crew. So I kind of shifted from being a payloads guy now to on the flight crew side.
Can I talk about you, Scott? You think of all the thousands of people, okay? He was the first and only person from Kennedy Space Center to get selected for this position. The only one. And still to me, it's amazing. And we have another joke we used to talk about, because being an alternate would be, of course, if something happens to the prime payload specialist, Scotty would jump in. Okay, well, of course, we're very good friends with Ron and Sam. So every time they came down to the Space Center, he says, what happens if somebody kind of pushes you and you have break an ankle or something? That means Scotty flies?
They were nervous to come to the cave.
We always a running joke that these guys whenever come to the cave, something's going to happen to us, so they can let our friend Scotty
just tainted oysters or something. So, we're ready for Astro 2, launched in March of '95. This was, at the time, the longest shuttle mission flown, 16 days. It had an extension kit on. Highly successful science observatory platform. And it's just a beautiful looking payload. And again, you got to keep in mind, this is about a 5-ton object being pointed at that 1 arc second, that diamond a mile distance, while the orbiter is going around at 17,500 miles an hour and doing its business. It's just amazing, and on all with 70s technology. Some fun pictures on orbit. This is Wendy and Borneo. They would, we got shifts like we did on Astro 1. The pilot or mission specialist would orientate the orbiter in the correct attitude. The mission specialist would activate and kind of point the IPS and lock it onto its target. The payload specialist, and I'm generalizing here, would configure the telescopes to the proper settings that they want, and off you go for an observation. Rinse and repeat for hundreds and hundreds of targets. And while that's going on, the ground is doing its business. Here's the Whoopee team with a sense of humor, enjoying themselves. I think this is near the end of the mission. That's myself on council. So this was at the POC. So you have the team that's operating if you will, the general operations of science, then the individual science teams. And we talked about changes. Look at that. That's the change paper that we telefaxed up. Despite your best laid plans, if you launch 1 second late or your orbit's just off by a fraction, you got to change things. Or the scientist sees something new that needs to be improved upon. Oh, change the filter from 7 to 8, et cetera, et cetera. And there's the flight crew picture. What a great shot. A couple more. I mean, the money shots go on, but imagine the joy of while you're exploring the universe, you're looking back on Mother Earth and that scale of, I'm looking at, galaxies that are thousands of light years or whatever out there versus here's our humble little blue dot that Sagan refers to. So, what was the results of this? Well, that's a whole other presentation for a future time, but these are all the targets, UIT and Haddad. You could go on, and you can get with me or JD afterwards, but I will share one. And this one was just short of getting a Nobel Prize, and I mean that sincerely. The Hubble telescope, in fact, was specifically designed, this 1 meter telescope with a super sensitive UV detector, a spectrometer, that their prime target was to use this distant quasar that was redshifted so much that it put it into the ultraviolet, that it kind of looked through the interstellar medium. What's all this stuff in between it? So think of this is a flashlight, and you have the detector here, and you can look at the spectrum, and it tells you something. Well, there was something called a hypothesis of the helium abundance. I think I've got that right. It was a ratio, I guess, of hydrogen to helium during the forming of the Big Bang. Up to that point, it had been a model of simulation. Here's what we think it should be. Hut sat on this quasar for over 20,000 seconds over 12 shuttle points. They got every instrument got a third of the observing time, and they spent a bulk of theirs on this prime target. And you could see, and I think JD would echo this, Art Davidson, who was the PI, each day his smile got a little bit bigger and bigger because he saw what was happening with the data. And it's all about accumulating lots of photons and reducing your signal noise. At the AAS meeting, which was about a half year later, he revealed the results. The model expectation, it matched the actual observation out to some amazing, 6 sigma. It was just spot on. It, at the time, was another confirmation of the Big Bang theory that if this really happened, this ratio of these two gases would be a certain number. And it was that, to many decimal places. And that's what science is, right? You've got an idea, you have a hypothesis, and you go validate it. That's what Astro did. I'm going to share one story really quick, and this is my favorite story with Ron Parise. Ron was an avid amateur radio operator, ham radio, you've heard of it. Well, it turns out Astro had the shuttle amateur radio experiment. It isn't the first time it flew. It flew actually with Owen Garriott on Space Lab 1. But Ron wanted it on board, and so we're doing these observations that we've all been talking about. Well, TDRS, which is a satellite that keeps us in comm with the astronauts, occasionally there's a window where you don't have comm. And it's for about 7-8 minutes, depending on the orbit. And that's the time when everybody runs to the bathroom, right, at the ground. And maybe for the crew too, okay? And so I'm at the mic, Astro Huntsville for Ron. We're coming up on a TDRS handover. Frank Bauer, a guy on the UIT team, calls in my ear. We have these little headsets, and he goes, Scott, they're flying overhead of Huntsville. Tell Ron to turn on the ham radio, and we'll talk to him. Well, I can't call that up, the GSE would go ballistic. So in the moment, I'm glad I didn't have time to think about it. I said, Astro Huntsville for Ron, one last thing before we go over the hill, I need an item 4 SIR enter, thank you. Well, all the commands to the computers are item entries and numbers. I just sent up his call sign for SIR. And he knew, That's ham radio. Well, everybody in the POC is going, wait, what's that? What command is that? And they're looking at me, I go, don't worry. And I calmed them down, so they all run off to the bathrooms and the things they do on the ground. Sure enough, Ron got some ham radio. He contacts the Huntsville Amateur Radio Club. They patch it in with a phone patch to the console and patched up into my ear. So I'm able to chat with Ron now, independent of the billion-dollar NASA infrastructure, and have a chat, informally with my friend and fellow crewmate. And so we banter, how's it going up there? How's it going on the ground? Well, again, don't give me time to think about things. Right before I had to sign off and we were going to get acquisition, I had the numbers and parameters for the next target. You know that changes that we talked about that you had to telefax up? Well, I told him those numbers and parameters, and he knew where to go with this. So I gave that to him, and we signed off, and everybody comes back into the POC, and I get the message that we're reconnected up. So Astro Huntsville for Ron, we're back with you on Tidris East. And he goes, okay, copy it here, Scott. And then I replied, Ron, when you're ready to go, I have the parameters to call up for you for the next target. He comes back, well, Scott, during that pause, I've been thinking we need aperture 4, filter 6 with an exposure of 800. And he whips off the numbers. And again, the heads, like little squirrels, look up. How does he possibly know that? There's no human way. And I just look, hey, you give the crew a few minutes to think on their own, they're going to come up with this. There were people bugging me about that for years afterwards that it bothered them, that they knew about it. And it was at Ron's celebration of life. He passed away sadly many years ago. I shared that story, and there were people out in the audience who goes, that's how they did it. So that's another behind-the-scenes story. So we're going to segue on you. Can you bring up the next presentation, please? So we've told you about Astro 0, 1, and 2. Now we're going to tell you about Astro 3. And this is the Astro renovation project. At the end of Astro 2, sadly, there was supposed to be an Astro 3. In fact, I was pulling for it because I would have gotten to fly. Sadly, it was canceled. When they ended the Space Lab program, the hardware was accessed and sent to the 4 winds. The telescopes were returned to the experiment developers. So Whoopi back to Wisconsin, UIT to Goddard, and Hutt back up to Hopkins. But Mikey, I, and others in the audience here, we're Space Lab guys and gals, and we said, it's a shame that this hardware is being accessed. This is part of our space science history. And so, at the time, when it's being sold for scrap metal, we went and grabbed as much as we could of Space Lab. And I mean that sincerely. We bought lots of stuff, either directly from NASA, again, it's through the disposition process, or from junk dealers who got there ahead of us. And so we accumulated this with the thinking, someday, i.e. when we retire, we'll get the band back together and see if we can put together some of these payloads. So we formed, on our retirement, a 501c3 called the Astro Restoration Project, and it's a labor of love. We're putting Astro back together. We have about 45 members, and all of us either work directly on Astro or another Space Lab mission. Myself as the president, a Teledyne Brown guy up in Huntsville, Maynette Smith, some of you may know her, Louis Delgado, who's here, and Mike Haddad is our chief engineer. And we're working up at the Huntsville U.S. Space and Rocket Center, putting this back together. And we've already talked about Space Lab, so I don't need to go through this. But here's kind of the timeline. The final mission was in '95. Space Lab ended in '98. We formed our organization, so we collected the hardware here. In 2020 is when we formed. And we did this with an agreement, I'll call it a handshake with the Smithsonian. The curator at the time, her name was Valerie Neal, and you may know her. She was back involved with Astro, and she was at the Astro 25th reunion up at Goddard, and I mentioned her, hey, by the way, we've got most of the mission peculiar hardware, including the cruciform and the optical sensor package for Astro. We know where the telescopes are. Would the Smithsonian like to get this all together and we can put together a team who built it originally or assembled it and tested it to do it again. She loved the idea. And so she retired. Dave Dvorkin followed her up and carried on the partnership. And that's when we formed. And their suggestion, which was a good one, because the Air and Space Museum is going through a major renovation on the National Mall, they said, look, if you can do it in Huntsville, it'd be better for you. We love the idea because half of our team is there. It's closer to us here at the Cape. And we're a living exhibit up there now. We are reintegrating Astro back on public display. And we've now created partnerships for STEM and also engineering aspects. Mikey, you want to touch a little bit on how we acquired the hardware?
Yeah, sure. You kind of see a couple pictures here. The one on the bottom right is actually the cruciform and the hardware and the cabling, some electronics. That was a shipping container that we discovered it was in, and we were able to basically that's what we saw and came and opened it up, and of course all that hardware was inside.
Where was that?
This is actually what, in Huntsville, right?
Yeah, they're Arab Huntsville. A junk dealer bought this for the aluminum. You know, this is the cruciform. This is that precision orthogrid structure. Probably cost millions of dollars. He bought it for junk. A little bird told me this was sitting out in the junkyard. I drove out there and I said, I want to preserve that. He says, pay me scrap metal value. I paid $1,500 for this.
Wow.
But then, how do I move a 3,000-pound structure? So this is myself up there and Shirley. We're tearing down the box, and Byron Bonds had a brother-in-law who owned a machine shop down the road, and he drove down with a forklift. And we lifted that up and put it in storage. But it had taken a toll. This is the cruciform right there, and that's Mikey loading up stuff at my house, and that we'd saved this hardware, and it all went up to Huntsville. And so through November 2020 through 21, we restored the cruciform. We took off all this MLI, multi-layer insulation, cleaned the structure, and I've got some pictures here, just show how nasty this was initially.
You can see all the cable and electronics that was still integrated.
And we peeled back this MLI, and Mikey distinctly remembers when I pointed out the dead rat to him.
Dead rat, bird nest, you know, the dirt dauber.
Mud daubers,
They're all over the place.
Look at that. That's nasty, and that's not, you know, presentable. But we went through a major job. We took every blanket off, cleaned it, removed the damaged material. By the way, Simple Green works. and Smithsonian approved.
Yeah, well, you know, we needed help. I mean, we're engineers and scientists and all. We're not restorers. You know, so we got with the people who are, that's their job, is to restore this stuff, pristine levels, and they were the ones that kind of gave us a real big help on how to do this, how to clean it, what's going to clean it, not damage it, that kind of thing.
But it works. You remove that. In fact, that's Frank Valdez. He's with us today, sitting in the back of the audience. Lynn Ferris, I remember Lynn, she was the lead operations controller for the POC. So our local team and some folks here, we cleaned up the crucible. Here's kind of what it looked like initially and how it ended up with. And you know, there's hundreds of these little cells on the orthogrid.
This took weeks and months of refurbishment.
And then what do you do with cables? Well, we took a little liberty here. We started with toothbrushes, right? And we ran the numbers, and that would have taken something like 2.5 years. And we said, well, how about we take it out back and pressure wash it? Which you would never, ever, 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 ever do with cables. But for cleaning cables that never have to pass the electron, it was accepted.
Yeah, our goal was to try to bring this back to the pristine environment that it flew in. Of course, it's not going to fly, but we looked at it as that way, saying we want to make this look like it did when it flew in the 90s. And so that was basically the goal of one way of cleaning those cables.
And here's us starting to install some of the avionics, the electronics and the cables going back on there. So it's coming back to life. Attention to details with drawings and documents. In fact, this is Mikey with the Marshall archivist lead. She provided us complete access to all the documentation. And then a true story, a little quick one, but it means a lot, I know, to Mikey and I. When she came out and saw how we were using the drawing, she kind of got tears. I said, are we okay? She goes, Scott, I've been doing this for decades. You see stuff come in, but you don't see use of it. You know what's happening at some level, or you know what may be used. This was the first time in her career that she saw the drawings that she had saved being used to make something real again, and it meant the world to her. Like, it does matter.
Yeah, these are 30-plus-year-old drawings that they digitized. And the process of digitizing took a lot of work, but nobody ever used them, of course. So we came and said, another quick story was, we had an engineer, Cheryl Lee, we saw in the previous one. She just by chance happened to say what was called a drawing tree. A drawing tree is one sheet of paper that lists every drawing for that mission. She saved that over 30 years, which was huge, because that one said, okay, for this is the drawing number, okay, for that item. And of course, we went to her, Marjorie, because she had on file the drawing number. So we gave her, these are the numbers we need for this hardware. She'd look up the numbers, she'd find them, they'd print us the drawings, and we used that to basically reintegrate the hardware. So we did basically what we did 30 years earlier, we repeated basically in the early 2020s.
So after we cleaned up the cruciform, we moved it from one building into their main museum hall. We're now a living exhibit there, and the public can come in and say, there's the bare cruciform. We haven't put any of the big science instruments on. The first thing we did, and we started the next phase, is we installed Whoopee. So Mikey and I went up to the University of Wisconsin, and we negotiated the loan of the Whoopee instrument, brought it down, and with our team integrated that. Here's it showing up. Still in the horizontal. Mikey mentioned earlier, remember, it gets shipped horizontal, and then we lifted it vertical.
They kept this GSE for 30 years.
Yeah, we hung on to the
It was in
GSE.
a warehouse somewhere.
That's that blue structure there.
Yeah.
It's the same one.
Same blue structure. And the optical sensor package, I bought this from a junk dealer in MIMS. I was up there buying some other hardware, and there's a big box and it said OSP. And I thought, oh my God, and I went over and kind of, yeah, there's something in there. I like this box, what's in there? And I told them, I said, it's called the optical sensor package. It was on a mission I supported, I'd like to preserve it. How much does it weigh? We estimated the weight. He said, I can't remember, I said $1,000 or something. Happy to buy, pay cash. Call a friend with a big pickup truck, and we hauled it and stored it in a hangar in Merritt Island for 20 years. And now it's back, fully integrated here.
Wow.
Yeah, one thing about that red bracket, just real quick, I know we're running late.
Yeah.
That red bracket basically was the support bracket that went between OSP and the cruciform. This mounted to the OSP, and that whole thing mounted to the cruciform. Byron, the TBE guy, happened to be in a junkyard one day, and this was laying over in the grass. The guy bought it, and it was just, Byron goes, he looks at it, probably a half a dozen people on the planet,
If that.
knows what that structure is.
Sure.
He just happened to be in there, and the gentleman, so I just haven't gotten around to melting it down. And he says, I want that structure. Can you imagine us trying to rebuild this structure?
And it's special metal, it's Invar, and so to keep the alignment of things, when it heats up, two metals fight each other to keep the alignment. It cools down, they
doesn't change.
Yeah, and who knows what NASA paid. You see how funky that design is. But found it in a back 40. Here we're lifting the optical sensor package up and mounting that. And there's how it looks today. If you go up to the U.S. Space and Rocket Center, we have a featured display. We just put in a large movie screen back here, and we'll be doing projections. And we're working with the Smithsonian for the UIT and HUT loan, which may be deferred. We may have to wait till they finish the renovation work. We're partnered with the University of Florida. They're designing a display stand for us, which has pitch and yaw, which will be very cool. It'll look like the IPS. Albion for some outreach of science. You may or may not have heard of something called NASA Hunch. It's a partnership with high schools that allows hands-on work for students. When we're missing a bracket or a bolt or something that we just couldn't find, we give it to this group, and along with NASA mentors, they machine it for us. We give them the stainless steel, we give them the tooling material, they go off and they mill it for us, and it's flight spec. It's just amazing work that they do. And this is a little bit about it. And this is some of the work that they've done with their mentors. It's top notch. You can fly this stuff. In fact, Hunch makes flight hardware for NASA now.
They fly it on space station. There's hardware they've made that's on space station right now.
This is our partnership with University of Florida. I mentioned they're doing some display stands. In fact, in 2 weeks, we're going to go up and see the final design. One is a actuator linear system like this, pitch and yaw, and another one's kind of a cable system that does it. And we're designing it such so you can use it for display, but also stow it for shipping to ultimately the Smithsonian. We did have a 3D model of Astro. Again, this is the 70s and 80s. So the students have gone out and made that. In addition, the Marshall folks have helped us by doing some imaging scans. And the last thing I'll share is that we do have outreach. Whenever we're working on it, it draws a crowd, as you might imagine, which is great. So ARP 24 and 24 Beyond is what we do. We've got a lot of supporters. You can be a supporter too if you're interested. I've got cards, but it's simply astrorestorationproject.org, and you can go learn more. You can volunteer, or you can make a donation to help us continue our project. And so the last thing I want to do is, and I know we've just got a few minutes, is can you bring up the SAM obit, please? We wouldn't be where we were at with the success of the mission without both Ron and Sam and their contributions. And sadly, they're no longer with us. And one other astronaut, Mike Lounge, passed away in 2011. 2008, astronaut Ron Paris. I've known him my whole adult life, and John, as he just mentioned, JD and as Mike, so these guys are close to us. And Sam sadly passed away a little less than a year ago. And with the approval or the blessing of Stacy Irwin, who was Sam's last graduate student, she wrote a lovely obit. I'd like to read it and just step through a couple slides in memory of Sam. Sam Durrance is regarded by his colleagues, family, and students as a role model of remarkable character, admired for his intelligence, kindness, gentleness, selflessness, and humility. As an astronomer, Sam made several seminal discoveries in the field of exoplanet formation, very low-mass stars, and brown dwarfs. And over the course of his career, he published dozens of papers on topics ranging from planetary astronomy and astrophysics to adaptive optics and spacecraft operations. As a professor, Sam was a mentor to many. He inspired countless students to pursue their dreams and make their mark in the world. Lesser known is Sam's winding path to become a scientist and educator. As a young man, he left home and moved to Los Angeles, California to, quote, race cars, chase girls, and become an actor. True statement. He had several odd jobs then, including box making and olive packing. Then after a chance meeting with Richard Feynman, he was inspired to pursue a career in physics. He soon also directed his academic efforts toward realizing his dream and becoming an astronaut. At Cal State University, he earned his MS and BS in physics and went on to a PhD at University of Colorado in '80. Sam arrived at Johns Hopkins in '80 as one of the first members of the Hopkins ultraviolet team, which was led by Professor Art Davidson. Hud had been selected by NASA in '78 to make a space shuttle mission that we just talked about. As the principal research scientist at Johns Hopkins, Sam designed and built many spectrometers, detectors, and imaging systems, and made numerous observations of the planets and low-mass stars with ground and space-based telescopes. And notably, he was on the team that in '95 discovered a first brown dwarf, which was a big deal at the time. In '84, Sam was selected to fly as a payload specialist. However, due to Challenger, as you know the story now, but he fulfilled his mission twice. He logged over 615 hours in space and made hundreds of observations with the 3 telescopes, again, that we've discussed. After he left Johns Hopkins, he served as the Florida Space Institute, the University of Central Florida, and then the Florida Space Grant Consortium. In 2001, many of you may know this, he became the executive director of the Florida Space Research Institute here at the Kennedy Space Center. And I myself can re-engage working with him, so it came full circle. In 2005, he joined the Physics and Science Department at FIT, Florida Institute of Technology, where he engaged in cross-disciplinary research and provided students with unparalleled access to opportunities in astronomy and space exploration. His commitment to education and innovation earned him numerous awards, including the Presidential Distinguished Service Award, NASA Exceptional Service Medal, and the Space State Foundation's highest honor. Sam's dedication to science and service extended into every area of his life. He often gave talks to the public, to students, his church, repeatedly recounting his experience in space, and a frequent participant in KSC's astronaut experiences. After a diagnosis of Alzheimer's in 2021 and Parkinson's in 22, he retired as a professor emeritus at Florida Tech. He died peacefully near his home in Viera, Florida, in May 5th, 2023, at the age of 79. He's survived by his 3 siblings, his wife Rebecca, his 2 children, Ben, Susan, and 7 grandchildren. My life, I'm sure JD, Mike, and anyone who knew him knew he was an incredible man. I miss him dearly. So that concludes our presentation. We probably have just a few minutes for Q&A. Of course, we're available in the hallway for others who want to elaborate, but thank you for your time. You have a question, sir?
Yeah, a question from Mike Haddad. Mike, you described your work area as being 100,000 class clean room. Could you define that and tell us some of the mechanical things you had to go through to maintain that level of cleanliness?
Sure, 100,000 K is basically 100,000 particles per cubic foot. And so basically what you had to do is you had to maintain that level or less. So basically you wanted a lot of particles floating around. To accommodate that, usually the floor level was at 300, but the area around the payload was 100. Well, to do that, you had we had to, of course, put on the bunny suits. We had sticky mats. Actually, after you put the bunny suit on, you actually have to walk over sticky mats, so the particulate on your shoe, on the bottom of your feet don't go up there. We cleaned constantly. We had witness plates that monitored all that, so we make sure that we didn't go outside the spec. The air conditioning in that had turnover, I think it was 8 times an hour. So there's a lot of those things we had to put in place. Like I say, the face hoods, like the gloves, all that to maintain the hardware at pristine levels. And we had to do that all. And of course, you know, we'd spend 12, 14 hours in these bunny suits. Sometimes we wouldn't eat lunch or dinner because we were working so hard. And of course, it got warm, but the idea was you sacrifice that to maintain the cleanliness of the hardware. So that was just a few things that we did, yes, sir.
Any other questions? Yes, one more back from this.
John David, on that wild loop you had, that ops loop you had for the telescope run up from the POC, with all that activity and thousands of sightings being made throughout the mission, did anyone ever have time to go to the bathroom?
Well, it was that 7 minutes. Thank goodness there weren't 3 teachers up there at that time, because we had the gap when we couldn't communicate. And boy, you would never saw so many people run so fast.
I'll have you know, behind the scenes, when I was talking to Ron, as amazing as it was, I lost that 7-minute gap, and the next shift was a long one.
I was at GC out in Mission Control, and those gaps drove everybody crazy. GC.
Yeah. Very good. One in the back, please.
Actually, it's not a question. I just wanted to say, as somebody who's just watched launches and watched the shuttle land, you get to think that, oh, it's all clockwork, it's all very routine, it's business as usual. Hearing this shows you there's nothing routine at all. And so I just want to say thank you very much for sharing all of that stuff. It's kind of mind-boggling.
Well, thank you. That means a lot to us. Every mission has its stories and its people. It takes a village, right?
Yeah, even like Astro, it's a reflight. It had its changes, even though it was a reflight of the same hardware that flew. Then you figure out the ones that are actually completely different was a lot of fun.
All right, Mike Haddad, JD, thank you, and we appreciate your time. Mark?